Welcome to your next lecture on thermochemistry. In this lecture, let me point out first, you need a calculator. Make sure your calculator can do all the basic functions of addition, subtraction, multiplication, division. It will help if you know where your parentheses are so that we can put a expression in parentheses to do the math. In this lecture, I also recommend that you have a pencil and pen or paper with you so that you can write down notes, questions, clarifying bits of information, anything that will help you along. Hopefully we'll answer them before the end of this lecture. If not, please make sure that you meet with your instructor so that they can go over it with you before the assessment for this unit test begins. So let's get started. At this phase, you should already know what the phase change energies diagram looks like. On the parts of the phase change energies diagram, as you can see in this particular diagram, this is just a recap of the phase change energies diagram. We're going to be using that to do some calculations to find out how much energy is needed to heat solid, liquid, gas, to change a solid into a liquid, or a liquid into a solid, and a liquid into a gas, or a gas into a liquid. We will be using the MC, the Q is equal to MC delta T equation, and we will be using this equation, this formula, for all of your calculations. Remember that M is for your mass. The capital C is the specific heat of whatever the substance is. Remember, all substances have their own specific heat. And delta T is the temperature change. Okay? Now, for your assignments, we will provide you with the information you need to be able to not only do the calculations, but also to draw the diagram, which we're going to get into. If you look here, you see that we have a chart for you. And let's look at the parts and pieces of this chart to begin with. First of all, the material. If you'll notice, there are 4 types of material: mercury, ethanol, nitrogen, and water. In the next column, it gives you the melting point. And if you look at the diagram up here, where freezing and melting occurs, this is where you would put the information for the melting point. And I'm going to do this in different colors because it makes it a little bit easier to understand. The next column gives you the boiling point. And when you look at the phase energies diagram, notice that where condensing and boiling occurs, that's where the boiling point would be. This is for all the solutions that we'll be giving you to calculate. Now let's get into some specifics. We already know that all substances have their own specific heat at which you can heat them up. So specific heat would apply to how much energy, how much heat would have to go into heating up a solid. That is the specific heat here in this column. This tells you how much energy and heat per gram goes into heating up. Remember, it's 1 gram, 1 degree Celsius. So this is the number of calories is required to heat up 1 gram of that substance, 1 degree Celsius. And we would use that for the calculation of heating up the solid. Then we have what we call fusion. I call that HF. That is the heat of fusion. That is the heat necessary for freezing to occur or melting to occur. And fusion is the amount of calories, again, the amount of heat per gram for this to occur. So this column is important also. Notice that these all coincide with your phase change energies diagram. The next column is the specific heat of heating up a liquid. Here on your diagram, you have where liquid is heated up. So this would be CL, which is specific heat of the liquid phase of that particular substance. And then, of course, if we're going to heat up the liquid, then eventually we're going to want to boil it or go from a gas and condensate back to a liquid. This is the column of HV, which is called the heat of vaporization. And then finally, of course, we're going to want to heat up the gas to whatever temperature they're asking for. So this is the specific heat of those substances in gaseous phase. Now, this information will be provided for you as you do your problems. I recommend that once I show you how to do your problems, you continue to do problems until you get very comfortable with it and you know that phase energies diagram pretty much by heart and where to put these numbers. So take a moment, either take a picture of this or take a moment to write it down so you know where all those parts are. Remember, we correlated all these parts on this chart to the phase energies diagram, and that is going to help us do those calculations. Okay, so on a normal diagram, you're going to have to do a couple of things. You're probably, in some point, going to have to draw the phase energies diagram itself, which is going to look something like this. Not necessarily with these numbers, because these numbers are specific to, I believe, ethanol. But we're also going to ask you a series of questions. Notice in the question box here, we ask you a series of questions. We give you the amount. We give you the starting point. We may even give you the ending point. And then we ask you questions about how much energy is necessary to heat up the solid, how much energy is necessary to melt the solid, how much energy is necessary to heat up the liquid, how much energy is necessary to boil the liquid, how much energy is necessary to heat up the gas, and then what is the total amount of energy that was used to do this heating. Whether we go from gas all the way back down to solid or solid up to gas, we're still going to use the data that happens to be in this chart. All right? One last thing before we get started. When doing our calculations, you need to look at and remember a few things. When I'm heating up a liquid, or solid rather, notice that I'm also increasing the temperature to heat that solid. Note also that I'm using heat energy to heat that solid. That means that for this calculation, I'm going to need to use my formula. And I have a formula that once I'm given the mass, which we already said they will give to you, I now have the mass necessary. I have the specific heat of the solid, which would come from here. And I have the temperature change, which is whatever the beginning temperature is to the ending temperature in heating up that solid, which gives you the MC delta T. And I have that same calculation for the liquid as well as for the gas. All of them are going to require a temperature change. All of them have a specific heat for heating them up, and all of them have a mass that have been given. When I get to the freezing, melting, or the condensing and boiling, things are a little bit different. When I get to the freezing, yes, there is definitely heat energy being applied. Yes, I have the mass that's been given to me. But notice that there's no temperature change. I'm just going to write that. No temperature change. So how do I go about calculating the freezing or the boiling or the condensing or melting? Well, that's when I now have to turn to the heat of fusion, or I turn to the heat of vaporization. That takes care of it for me. Here, all I need is the mass and the heat of fusion, and that will tell me the amount of energy that goes into freezing or melting this substance. Up here, I need the mass for condensing and boiling, and I need the heat of vaporization. And that will allow me to calculate the amount of heat that goes into boiling or condensing this substance. Again, take a pause, take a picture, write it down as you need see fit. Okay, let's go ahead and get started. This first one is a phase change for nitrogen. Now, because the chart is not on here, I'm going to supply you with that information. We're going to do two problems like this. And then we're going to do two problems where we're going to have to draw the chart and do the calculations ourselves. So for the first one, notice that we have a phase change energies diagram for nitrogen. At the bottom of this, it gives us the information we need. Let me do that in this way. It tells us that we are given 500 grams of nitrogen, so that gives me my mass. And it tells me I need to find the energy for each phase, or the total energy for input if I'm going from a negative 250 to 20 degrees above the boiling point. So whatever the boiling point is, I'm going 20 degrees higher. So let's go ahead and get our diagram put together. Based on the information from the chart, I'm going to supply you with the melting point. Put that here. And the boiling point. Remember, the melting point and the boiling point are how we determine the shape, actually, of our phase change diagram, whether it's long, whether it's short. Here's my solid, there's my liquid, there's my gas. There's my freezing and melting point and my boiling and vaporization point. So all I need to do is put my data where it's supposed to go. According to my data, oh, and here's, of course, the formula I'll be using. According to my data, the melting point for nitrogen is a negative 210 degrees Celsius. The boiling point for nitrogen is a negative 196 degrees Celsius. According to my instructions, I'm going to start it at a negative 250, and then I'm going to heat it to 20 degrees above what the boiling point is. Well, if this is my boiling point right here, 20 degrees above that is going to give me a negative 176. And if this is my freezing point here, and I'm starting at a negative 250, that means that my negative 250 is going to go here. Right? The first thing I'm going to do is figure out, all right, at a negative 250, I have to heat my solid. So I'm going to have to use my energy formula to heat my solid. I know the mass is 500 grams. I know the specific heat which is going to be given to me. And I have to figure out what my temperature change is. Okay, well, since I'm going to give you the specific heat, let's figure out what the temperature change is. Your temperature change is from a negative 250 to a negative 210. So your delta T is going to be a difference of 40 degrees Celsius. And that's what I'm going to plug into my delta T. My mass, I'm going to plug into my M. And then capital C is my specific heat for that solid that I'm going to get from the chart. So let's see what that looks like. There it is. All the parts and places are put in place. This is my mass, which was given me. This is 0.39 calories per gram degree Celsius, which is from the chart. And remember, that's the specific heat of my solid. And then this is 40 degrees Celsius, which is my delta T, which is going to be equal to 7,800. So take your calculator, make sure I'm correct. Clear your calculator, put in 500 times 0.39 times 40 equals, and you should get 7,800 calories. Pause this if you need to make sure you understand it, and then come back to it. Alright, so there is my solid. Now, let's look at my freezing and melting. We said in freezing and melting, which starts here at a negative 210, there is no temperature change, but there is an energy change. So this is only going to require the mass that I'm given already. And we said this would be heat of fusion, which comes from your chart. There is no delta T, so this is going to be equal to my energy. So let's go ahead and plug that information in. So here we have my mass, and this is my heat of fusion for nitrogen. 500, clear your calculator, 500 times 6 should give you 3,000 calories. All right, so now I've got my solid, I've got my freezing or melting point. Now I have to heat up my liquid. My liquid is going from a negative 210 to a negative 196. So use your calculator, see if you can calculate what that difference is going to be. If you came out with delta T is equal to 14 degrees Celsius, you're absolutely correct. So that's our delta T. So now I have my mass, which is given. I can look on my chart. It will give me the specific heat for the liquid nitrogen. And then I have delta T, which we've just calculated. So let's put that all in place. And here I wind up with 500, clear your calculator, got 500 times 0.474, which is the specific heat of the liquid, times the temperature change, delta T, which we calculated together. And that should give you 3318. Pause if you need to and come back. Now that I've got my liquid, solid, melting, and liquid calculator, now I have to look at my boiling and vaporization. Again, while there is a movement of energy, there is no movement in temperature. So once again, I'm going to take the mass that I'm given times the heat of vaporization this time. And that is going to give me the energy needed to boil that liquid nitrogen. So when I plug in my numbers, I take 500 times the heat of vaporization, which is 48, which is going to give me 24,000 calories. And lastly, now that I've done all of these, I've heated the solid, I've melted the solid, I've heated the liquid, I've boiled the liquid. Now I have to heat my gas 20 degrees higher than the boiling point. Since this is being heated up, there is a temperature change occurring here, as well as energy occurring here. This is my mass of 500 times the specific heat of nitrogen as a gas times my delta T. What's my delta T? It tells me that it's 20 degrees above the boiling point. So my delta T is going to be equal to 20 degrees. And when I plug all that in and set it up, I have my 500, or my mass. I have my specific heat of gas nitrogen, and I have my 20 degrees delta T. Clear your calculator. Take 500, multiply it by 0.248, and times 20. That will give you 2480 in calories. Okay, so I've heated my solid, melted my solid, heated my liquid, boiled my liquid, heated my gas. My question now is, what is the total energy input? Well, the total energy input is going to be adding all of these together. So clear your calculator, put in 7800 plus 3000 plus 3318 plus 24000 plus 2480. If you add them all together, you should come up with 40,598 calories. Again, you're just adding them all together. And that gives us the total energy input, because that was your question. Now, what if I'm giving you calories and I tell you I want it converted into joules? Well, that's simple enough, because we know that 1 calorie is equal to 4.184 joules. Since I know I have 40,598 calories, all I would do is multiply this by 4.184, and that is going to give me the joules. Pause the video, make sure you understand it, rewind it as you see needs fit, and continue on when you're ready. Okay, so let's look at the second one. This time, I'm given 200 grams of water. So this is not nitrogen. This is actually water. To find the energy for each phase, I need to know the total input. My water is going from 25 degrees Celsius to 30 degrees Celsius above the boiling point. Okay? So, again, remember we have the melting point in the chart. We have the boiling point in the chart. And we'll give you that, though you should know what those are by heart anyways. They'll surprise you once we go through. Okay? And remember that in our calculations, since this is solid, this is liquid, and this is gas, whenever you have solid, liquid, and gas, there is always going to be an increase in temperature as well as an increase in heat, which means to heat up solid, liquids, and gas, we would use Q, or heat, is equal to MC delta T. This is because we have to use a specific heat of the solid, liquid, and gas, the mass that has been given us, and of course the delta T, or the temperature changes that occur. When I'm dealing with the melting and boiling, remember here, while there's an increase in my heat, there is no increase in my temperature, so that's simply going to be the mass times the heat of, in this case for melting and freezing, heat of fusion, and for this case in boiling and condensation, it'd be mass times heat of vaporization. Just a quick review, so let's go ahead and get ourselves started. There's my solid, my liquid, and my gas. There's where my melting is. There's where my freezing is. Now, if you look on the chart, and I'm supplying you with it right now, but we should remember that the freezing point of water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. This says that I'm going from 25 degrees to 30 degrees above the boiling point. Well, 30 degrees above the boiling point is going to be about 130, because the boiling point is 100. And 25 degrees, well, if this is 0, then 25 degrees is about right here. Okay? So that means the only thing I'm going to be interested in then is this part, because they've given me 25 degrees Celsius, which is a liquid version of the water, and I'm heating it up to 130. Keep that in mind. So, there's my points for 25 and 130. So, how much energy does it take to heat the solid? I don't have a solid, right? Because this is where it starts. So that would be 0. And how much heat does it take to melt that solid? Well, if you don't have a solid, you certainly cannot melt it. Again, it doesn't start there. But how much heat does it take to heat the liquid? Well, if this is starting at 25, then I do have 25 degrees here. And I know boiling point is at 100, so my delta T is going to be 100 minus 25, which is 75 degrees Celsius. So now I've got a temperature change. I've got a mass. I've got a specific heat, which you guys should know by heart, and I've got a temperature change, so I can calculate that out. And that is going to be 200 from my given. The specific heat of water is 1. You should already know from the chart, and you should know by heart. And then your delta T is 75 degrees. And so that is going to be, clear your calculator, 200 times 1 times 75, which is 1,500 calories. So I've heated this to here. Now, how much energy goes into the boiling of that liquid? Well, since I'm going to go all the way up to 130, I do have to boil that. I know the mass. There is no temperature change, so I'll be using the heat of vaporization for that to get the amount of heat I need. And the setup is 200, which comes from the mass that I've been given. 540 is the heat of vaporization for water. If I take 200, multiply that by 540, that should give you 108,000 calories. So go ahead and do that. Make sure that that's working. And then finally, I have to find out how much heat is going to go into heating up this gas to 30 degrees, 130 degrees, or 30 degrees higher than the boiling point. Again, I have a temperature rise. I have a heat energy rise. I know the mass. I can get the specific heat of water as a gas. And I can figure out my delta T, which they give you, because they say it is 30 degrees. So, when I put my numbers in, I have 200 from what I'm given, 0.5 calories per gram degree Celsius is a specific heat of water in a gas phase, times 30 degrees, which is my delta T, is going to give you 3,000 calories. So that's how much energy it took to go from 25 degrees Celsius, heat that water, liquid, and go all the way up to 130 degrees Celsius. So I'm asked what is the total energy input. I'm going to have to take, just like I did before, the total of 15,000 calories plus 108,000 calories plus 3,000 calories. So clear your calculator. Put in 15000 plus 108,000 plus 3,000. Hit the equal sign and see if you got what I got. My answer is 126,000 calories. And again, if I said I wanted it in joules, since joules, one calorie is equal to 4.184 joules, I would just multiply this by 4.184, and that will give me my answer in joules. Okay. So we've been doing all those for you. Now this time, we're going to do everything. We're going to draw, we're going to find our boiling point. We're going to find all that. We're going to do all those calculations all by ourselves. We're going to draw the sketch all by ourselves. So if you're ready, I'm ready. Let's go. Okay, so let's look at it. What am I given? I have 250 grams of nitrogen. So I know that that's what my mass is going to be. And I know it starts at a negative 250. Okay, well the first thing I'm going to do is I'm going to draw my sketch. Now I have the sketch drawn on here for you, but we're going to put the parts of it together. First thing I'm going to do is I'm going to place my melting point. The melting point, here we go, for nitrogen, because that's the one I'm looking at. My melting point for nitrogen is a negative 210. My boiling point is a negative 196. This says that I started at a negative 250. Oops. Okay. So I got my melting point, got my boiling point. I know where I start. Okay. Now my recommendation is always that you read all of it so you know what you're drawing. But some people just take it step by step. Me, again, I read all of it. So it says how much energy is needed to heat the solid. So I know I'm going to need to heat the solid. I need to melt the solid. I need to heat the liquid. I need to boil the liquid. And I need to heat the gaseous nitrogen to 20 degrees above the boiling point. Well, if this is negative 196, which is my boiling point, then 20 degrees above that is going to be a negative 170. What is that? Stop. 76. Forgive, my cat is interfering. Let me write that a little bit clearer. Negative 176. Okay. So let's do the first one. We've got our sketch done. How much energy is needed to heat the solid nitrogen? Well, let's look. This is my solid. I don't worry about these anymore. And it's going from a negative 250 to a negative 210. What's the difference between a negative 250 and a negative 210? That is 40 degrees Celsius. So since I am increasing in temperature, then I know I'm going to need to use the MC delta T for this. So I'm going to take what I'm given, which is 250, times, I need the specific heat for solid nitrogen, which is right here, and that's 0.39, times my delta T, which is 40 degrees Celsius. So in your calculator, take 250 times 40 times 0.39, push the equal sign, and you should get 3,900 calories. Okay, so now I want you to write that down because you're going to have to keep track of it. I have no room. Of course, I might be able to put it right here, 3,900 plus. Might type it that way. Okay, let's look at the next one. This time, I need to heat my solid. So, since I'm heating my solid, there is no temperature change. I'm just going to use the M, and I'm going to use the heat of fusion because it's melting and, freezing. So, heat of fusion for this is 6. So, I know my mass is 250 times my heat of fusion, which is 6. And your calculator, clear it, 250 times 6, you should get 1,500 calories. Okay, so I'm going to add another 1,500 calories to what I have. Okay. So I have heated it, the solid, and I've melted the solid. Now I need to heat the liquid. Well, the liquid is going from a negative 210 to a negative 196. My temperature is changing, so I have a delta T. And the difference between 210 and 196, you can calculate that, is going to be 14 degrees Celsius. So my mass is 250 times, I'm going to need the heat of heating that liquid. So I find my specific heat to be 0.474 times my temperature change, which is 14 degrees Celsius. So clear your calculator. 250 times 0.474 times 14 is going to give me 1,659 calories. So now I'm going to add 1,659 to my list. And that takes care of how much was needed to heat the solid. My next question is how much is needed to boil, not the solid, but the liquid, to boil the liquid. Again, there's no temperature change, so I'm just going to use the mass, and this time the heat of vaporization, not the heat of fusion, but the heat of vaporization. So this is going to be 250 times 48. So clear your calculator. 250 times 48, which should equal to 12,000 calories. So now I'm just adding 12,000 calories to my list. Okay, we got one more to go. Finally, I have to heat my gas, and it tells me that I'm heating it 20 degrees above the boiling point, so I already know what my delta T for this is going to be, and that's going to be 20. There is temperature change, so I know that I'm going to have to use the MC for gas, delta T. My mass is 250 times my specific heat for heating gas, which is 0.248, times my temperature change, which is 20. Clear your calculator. 250 times 0.248 times 20 is going to be equal to 1240 calories. So I'm going to add that to my 1240. There we go. All right, so let's look at all our numbers, because the final thing is, what is the total energy input for the problem? So I have 3,900. I have 1,500. I have 1,659. I have 12,000. And I have 1240. If I add these all up, my answer should be 20,299 calories. Add those up, double check them, and then come back. Okay, so if I know that I have 20,299 calories, and I want to convert them into joules, I would multiply this by 4.184, and when I do that, that is going to give me 84,931.016 joules. Are we always going to ask you to convert into joules? Absolutely not. But should we ask you to convert any of these numbers to joules, you should know how to. Okay? All right. I think we did pretty good. All right, let's do one more, because why not? All right. So one more. There we go. This time, we're dealing with water. We have 500 grams of water, and it's at 20 degrees to be raised to 90 degrees Celsius. So let's first find our melting and boiling point. This is our melting point. This is our boiling point. When we find water here, we find our melting point is 0 degrees. Our boiling point is 100 degrees. Okay, and according to our instructions, we're starting at 20, which is about right here. That's 20 degrees Celsius. And we're going up to 90, which is about right here. So that's 90 degrees Celsius. So we're only interested in this section of the chart. Okay, so let's get started. Sketch the temperature and time graph, which we just did. How much energy is needed to heat the solid? Well, there is no solid, right? Because we're starting our temperature right here. It starts at 20 degrees. There is no solid. So that's 0. I'm going to put a 0 here. Then it says how much is needed to melt the solid. Well, we're starting at 20 degrees Celsius. So there is no melting of the solid because we have no solid. So that's also 0. Okay. Then it says how much energy is needed to heat the liquid water. Well, do I have liquid water? Oh, I do, right here. So I know my delta T is from 20 to 90 degrees. So my delta T to heat that is 70 degrees Celsius. I have a mass, so I have 500. I am heating liquid, so the specific heat for liquid water, which you should know by heart, of course, is 1, times my temperature change, which is 70. So clear your calculator. 500 times 70 times 1 is equal to 35,000 calories. So I'm going to put my 35,000. Okay. Then it says how much heat is necessary to boil the liquid water. Well, there is no boiling because it boils at 100 degrees Celsius. And I'm only going to 90, so that's 0. And how much energy is necessary to heat the gaseous water? It stops at 90 degrees, which is a liquid. So there is no gas because there was no liquid to boil. And then finally it says what is the total energy input? Total energy input is the 0 from heating the solid plus the 0 from melting the solid plus the 35,000 from heating the liquid plus the 0 because there's no liquid to boil, there's no boiling going on, and plus 0 because if there's no boiling then there's no gas. So my answer to this is equal to, after I add these all up, of course because you got to add everything up, is going to be equal to just 35,000 calories. Okay? And now that I have my 35,000 calories, if I wanted to, of course, convert 35,000 calories into joules, I would simply multiply it by 4.184, and that is going to give me, give me a second, 146,440 joules. So 146,444 joules from 35,000 calories. Pause it if you need to. Write any questions you have. Okay? And that ends the lecture. Please make sure that you go back over these. You don't need necessary new problems, but go back over the ones that we've done. Make sure that you understand them. Write whatever questions you have that didn't get explained in the lecture, and make sure you see your instructor.